So let's talk about a method that could make integration much easier called partial fraction decompositions. Now take a look at this expression here. It's the sum of two rational functions. In the numerator you just have a simple constant, and in the denominator you have polynomials of degree 1. If you add these two terms together by getting a common denominator, you end up with this polynomial. Now if you run into this integral here, which just has that polynomial that you see over there, it looks pretty hard to integrate. Even with a u substitution you could get in trouble. But if you do the partial fraction decomposition, you basically go in reverse. This integral is much easier to integrate. And that's the basic idea of partial fraction decomposition. So we're going to need some definitions. So a rational function is said to be in reduced form if they have no common factors in the numerator and denominator. Basically, if we start with, say, that polynomial that you see up there, okay, but instead I multiply it by, say, x minus 2 there, you could see that we'll get a 3x x minus 2 all over, and if we factor the denominator, we get that term here. And what basically a common factor means is that, okay, so reduced form does not have that situation going on. Okay, you cannot in a sort of formal way, the greatest common divisor between the numerator and denominator is 1. Also, a rational function is said to be proper if the degree of the numerator is strictly less than the degree of the denominator. So for example, x plus 1 over x minus 1 is not proper. Okay? But x plus 1 times, say, x minus 4 all over x minus 1, x minus 1 times x plus 4 times x plus 3 is proper. Okay? And that's because the numerator has a degree of 2 and the denominator has a degree of 3. Okay? And they don't have any common factors, so that rational function there is proper. Okay? So let's look at this theorem, which we'll be using. Any rational function can be written as the sum of a polynomial and a proper rational function. You have this polynomial here. This is just using Euclidean division, the remainder theorem, to basically, you could write out any polynomial in this form where you end up with a remainder and the degree of the remainder is strictly less than the degree of q. And if you take q and divide it on both sides, well, then you have this rational function written as a polynomial plus a proper rational function there. And how this is done, if we take, for example, we're dividing x minus 1, we're dividing x plus 1 by x minus 1. Now, how many times is x going to add? Well, that's 1. And so you'll get x minus 1 and a remainder there. If you subtract these two, you'll get a remainder of 2. And so that means x plus 1 over x minus 1 is equal to 1 plus 2 all over x minus 1. And so while x plus 1 over x minus 1 was not proper, this term here, okay, you have a polynomial of degree 0, just a constant, plus a proper rational function. So let's look concretely at the partial fraction decomposition method. And so if you do have a rational function that is proper and in reduced form, again, the degree is of the numerator is strictly less than the degree of the denominator in reduced form, so they don't have any common factors. And if we assume that the denominator q has been factored completely over the real numbers, and m is a positive integer. Okay, factored means you pull out as many simple factors that look like x minus r. So you do that as much as possible. Some polynomials can't be factored over the real number, and we'll discuss that possibility. Then for any factor in the denominator that looks like x minus r, you write out a partial fraction for it. That's a, where a is a constant, okay? A is a constant over x minus r, the factor in the denominator. Sometimes you don't get just a simple linear factor, you'll get a repeated one. And so you have a degree strictly greater than 1. Well, what do you do in that case? You write out, starting from this constant a1 over x minus r to the power 1, you keep increasing powers of x minus r, okay? So this 2, and then you just write a different constant a sub 2, and then 3, a different constant a sub 3, all the way until you reach that power m. Okay, so you just keep adding terms that are constant divided by x minus r, taken to the power higher than the previous one and up to m. Well, what if we have a factor in the denominator that cannot be factored over the real numbers? Okay, in this case it's called irreducible. In what sort of partial fraction do we include for an irreducible factor in the denominator? We include this. Okay, so we'll have a, which is a constant, times x plus b over this irreducible quadratic. And what about if that irreducible factor was taken to a certain power other than 1? Well, in that case, we will have a1x plus b1 over that irreducible polynomial, and add, then we'll go to the next step, and then we're raising it to the higher power. And we do this all the way till we get to that highest power. And note that all of these a sub 2 and b sub 2 and a sub m and b sub m, all these are constants, and x is the variable there. So let's make this concrete with an example. So consider this integral right here. You look at it, you might try u substitution, but again, you're likely to get into problems. But do note that the highest power there is 2, and the highest power here is 3. So it looks like to be in proper form, and as long as we don't get in trouble with certain factors canceling out, yeah, then it is in proper form. And let's go ahead and factor out the denominator. We do so, and here are the factors. So notice that we have, you could treat x as sort of like x minus 0, okay? And so we do have a root at 0, and we have one at 2. The root at 0 is a repeated factor, and the root at 2 is simple factor, okay? Simple linear one. And so you'll just have, for the x squared term, you'll get these two, okay? So we're again repeating, this x minus r is 0 in this case, and it's a repeated linear factor, and so it goes up to 2, and so we have these two terms, which here we don't, instead of calling them a sub 1 and a sub 2, we just call them a and b. And x minus 2, well, that's a simple linear factor, and so we're just going to have that term added to our partial fraction decomposition. Okay, and so we end up with this. And now the game is to find what a, b, and c are. How do we do that? Well, we have that equation right there. Let's multiply that equation by x squared and x minus 2 on both sides. So we cancel these terms here, and we end up with that expression. Now we simplify it. And here, after simplifying it and canceling out, say when you distribute that x minus 2, it'll cancel with that one, and you'll be left with the x squared there in front of the c. But I leave these two expressions. I call this expression 1. And then I gather the terms based on the power of x that they're multiplied with. And I have this expression here. Okay? And I call that 2. Now, if we use 2, okay, then what is this equation, this left-hand side and right-hand side, telling us? It tells us here that we have a plus c multiplying x squared. Well, what's that multiplying x squared on the left-hand side? That's a 5. And so we'll have a plus c equals 5. Okay, and on the right-hand side, we have negative 2a plus b multiplying the x. Well, what's multiplying the x on the left-hand side? Negative 3. And so we get that equation. And likewise, we have negative 2b multiplying the x to the power of 0, or 1. And what do we have, that's similar on the left-hand side? We have 2, and so we get that final expression. Now you have a system of linear equations, and you just solve for these 3 variables, a, b, and c. Here it's particularly easy to do it because you just start from b there, and then you'll get that b is negative 1, and then you could use that other equation to get a this time, and then finally solve for c. And so you get that expression there, and we use 2. Okay, and it's easy. Now I want to highlight an important alternative. And that important alternative is you could view from equation 1. Now, the left-hand side equals the right-hand side for all x. Okay, so for any possible x, the left-hand side equals the right-hand side. But notice this trick could be used to solve for the constants a, b, and c much more easily. So, for example, take a look at 1. We could set x equal to 0. Now, if we do that, this factor goes away, and so does this factor. And 0 in place of here will just give you a negative 2, right? And so you'll have negative 2 times b, and now x is 0 here, gets rid of these factors, so you'll have negative 2 times b equals 2, okay? And that's how you're getting x equals 0. And just to write that out for the first x equals 0 concretely, so you'll get 5 times 0 squared minus 3 times 0 plus 2 is equal to a times 0, 0 minus 2 plus b, 0 minus 2 plus c, 0 squared. Okay, now this is 0, that's 0, 0, 0. And so you get from this, net 2 is equal to negative 2b, and you could solve for b being equal to negative 1. Well, if I also chose x equals 2, well, I could get these guys to be 0. And I'll get c times 2 squared is equal to 5 times 2 squared minus 3 times 2 plus 2. You could use that to solve for c equals 4. And the basic idea here is that, okay, we could just match the degree of x on the right-hand side and left-hand side, the coefficient multiplying that degree of x, or we could start choosing particular x's. And we're allowed to do that because this should be true for any x, okay? And so sometimes choosing a particular x could be a shortcut. Okay, here it didn't really bias too much because it was pretty easy to solve the system of linear, the system of equations there. But sometimes it can make your life much easier to choose particular x's and then solve for the coefficients. And notice in each time we're taking factors to 0. Okay, so when I use x equals 0, I take this factor and that factor to 0. When I use x equals 2, I take this factor to 0. Okay, and also this factor to 0 because you'll have 2 minus 2 there. And so that's the point of choosing particular values of x. And so we get we get the values for a, b, and c. And so we have that this rational function can be written this way, and now the rest is a piece of cake. We do that integral. It's basically, integrating 1 over x. We know that's log x, and negative 1 over x squared is 1 over x. You just think about the antiderivative there. And plus a constant. This is a constant. We're used to seeing c, but because we used c up here, we're going to use k. And we have our final answer. We could combine the terms. This is also a good final answer, but we could also combine the logs and have natural log of x times times x minus 2 in here. Okay. And so we're done with that problem. Let's take a look now at a second example. With our second example, we get an irreducible quadratic, okay? The rational function here is in proper form, okay? The degree of the denominator is 3. You could see that there, with the degree of the numerator is 2, so it is proper. There are no common linear factors, and now we're just declaring that, but checking it could be somewhat tricky. Okay, you'll have to factor and check, but here they are. This is in proper form, and it is, and there are no common factors, and so we're going to use the partial fraction decomposition. What does x minus 2 require? Well, a simple factor that looks like that on the right hand side. And what about this irreducible one? Well, let's go back and take a look. Okay, what does a simple irreducible quadratic factor have? You get a term in the partial fraction decomposition that looks like this. Okay, and so we're gonna write out a term in our partial fraction decomposition for the irreducible quadratic that looks like this. And then we do the same steps that we did above. You multiply by the denominator, and you get 7x squared minus 13x. That's not a b, it's a 13 plus 13 is equal to this term here. Now again, we could choose particular x's, or we could gather the terms that multiply the particular degrees of x. So x squared terms, you'll get an a plus b there, and then this will be for x, and this is the constant. And you'll have, this sort of not written here, but you'll have that this should equal this, and you'll have that 13 should equal that, and you'll have that 13 again should equal this. And you solve that system of equations, which is the same algebra that we did above, and you will get this. Okay, and so you could write this integrand, okay, as a partial fraction decomposition with the particular values for a, b, and c. So we get 5, that's the a, and b is 2, and so that's where that's coming from, and c is 1, and so that's where that's coming from. And you could split that integral. Now, how do we solve the rest? This one's a piece of cake, right? 5 natural log absolute value of x minus 2. Now this one we have to be a little bit more clever, okay? If you use u substitution, you'll get that du is 2x minus 2. Now up here we have 2x plus 1, so we can't quite sweep it under the rug. But we could do a trick where we basically write 2x plus 1 as 2x minus 2 plus another constant, right? 2x minus 2 plus 3. And so here I subtracted and added 2 because I want that 2x minus 2, so I could get that du, okay? In doing that, you'll be left over with a 3. That's where that term is coming from. This is just our original term here. And now we split up 2x plus 1 over this into these two terms, okay? And now I can sweep, so I'll have this be u, and then sweep the 2x minus 2 into du, and I have this 3 over this factor. Now, how do I deal with that? Okay, it's actually easier to deal with by completing the square. Okay, so we'll complete the square, and basically completing the square is getting rid of that x there and writing it in the form of x minus a squared plus some constant b. And we do now, I already used u, so I'm going to do a w substitution, if you will, and set w equal to x minus 1. And so you'll end up with that expression there. And now we can integrate all of this. You just got to remember that that's the antiderivative of this term is arctan, okay? And you'll get a 3 over root 2 if you integrate that. Okay, the root 2 is coming from the antiderivative of that. So for the arctan, it also has that root 2 at the bottom. Okay, and you end up with for d over u, you get that term here. Don't forget the u substitution, and this one gives you that term there. Okay, So a nice little trick. We had to complete the square at the end, and we did have to be clever with our u substitution, with being careful about what we could sweep under the rug of du. But like that, we are done at the end.